Hello, for today's lecture for EME 497 Geothermal Energy Engineering, the topic that will be covered is well completions for geothermal wells. Well completion relates to the measurements that are made during and following the drilling process and while the wellbore is undergoing heating. There are different types of test programs. For exploration wells, the test methods are undergone to determine the characteristics of the well, while for production wells, the test methods are undergone to determine the characteristics relevant to likely production of the well or its injection capacity. The ultimate test is the capacity of the well to deliver fluid to the surface or its capacity for injection. Some of the information pertinent to the well can only be measured in the period between the completion of drilling and the discharge of the well, when the well is completely shut in and gradually recovering from the drilling process. These tests reveal several properties of interest spread between reservoir and fluid properties and associated well characteristics. For reservoir and fluid properties, the information that is pertinent is local reservoir and fluid properties, real formation temperatures, deep-halt reservoir, overlying aquifers, fluid state, meaning pressure, temperature, and enthalpy information, reservoir state, either liquid or vapor dominated, reservoir permeability, reservoir chemistry relating to salinity, cation, and isotropic ratios. For associated well characteristics, the information that we look for is location of feed zones in the well, feed zone permeability and production characteristics, near well changes in permeability, physical condition of the well, which is information related to the casing line or open hole of the actual wellbore. The testing is done with a specialized test sequence. This is normally performed after final completions, but can be done intermittently to gain information at different depths. The type of drilling impacts the type of testing. The testing is normally performed by injecting cold water at different flow rates. The resulting pressure temperature spinner profiles reveal information that defines the location of feed and lull zones, defines characteristics of those feed and lull zones, defines when the well has more than one feed zone. In this case, more sophisticated interpretation is needed, and good data allows for characterization of those individual feed zones. In this process, the cold water is injected into the wellbore using a down-hole logging tool. This tool makes simultaneous pressure temperature spinner observations. Using a surface readout tool, the information is monitored, and if needed, any adjustments can be made. Accurate transformation of the spinner frequency data into a fluid velocity profile requires that there are at least two up and down profiles at different logging velocities inside the wellbore. This testing should be done over the whole open hole section for at least one of the injection rates. The testing should also be extended into production casing by 30 to 40 meters for data equipment quality checks. The previously discussed test is designed for a high permeable well. This is one where highly permeable fractures are expected, and the program looks for stabilized temperature and pressure zones. There are also low permeability wells, and they are done differently. The program is designed to follow transient temperature fronts to find lull zones. As mentioned before, there is a difference between wells that are highly permeable and wells that have low permeability. In high permeability wells, there is a difference between the cold pressure gradient in the well and the hot pressure gradient that is in the formation. In the high permeability case, the upper part of the well will be underpressurized with respect to the formation, so the flow will be from the formation into the wellbore. The low permeability case, on the other hand, is when the wellbore will be overpressurized everywhere in respect to the formation. This therefore results in the flow being from the wellbore to the formation. And here's some more information on high permeability wells. They have a characteristically steep temperature profile with an isothermal between the inflow zones. This can be seen on the graph on the left. The preferred test method is to measure 2 or 3 sets of stabilized temperature pressure profiles while injecting water into the wellhead. By changing the injection rate and the pressure downhole, it is possible to switch on and off the inflows from different depths. From this, you can calculate the formation pressures at the zones. You can use the heat balance equation to calculate individual zone characteristics. As previously discussed, low permeability wells are different than high permeability wells. Often there are several small fluid loss zones spread throughout the well. The most successful manner in which to find these loss zones is during the cold water injection. During this process, the well is allowed a short amount of time to heat, which is about 12 hours. A series of temperature profiles are made while injecting water at a low flow rate. The loss zones are marked by change of the temperature gradient. This can be seen in the graph on the left. In some wells with low permeability, the bottom of the well will continue to heat as the cold water is injected. This shows that part of the well is not accepting the water and is impermeable. It's a good method to discover the deepest level of permeability. There are some important quantifying reservoir parameters that need to be taken into account. There cannot be equilibrium between the well bore and the formation pressure. This is a result of the different pressure gradients between the cool and hot fluid. It is not always possible to interpret the data if there are issues with the testing program. These issues could be an incomplete program, measuring fallout data at the wrong depth, too strong of an internal zonal flow, or failure of instruments. When there is constant data, you can, however, create a fluid flow profile and find the information such as feed zone locations and injectivity. Productivity, also known as the injectivity index, are important. The equation is as seen on the screen below. The injectivity index can be calculated easily once the main loss zone is found. The evaluation of the index should be found as close as possible to the zone of highest injectivity. However, this might not be at the major loss zone. This is a result of the fact that the pressure difference between formation and wellbore increases with depth. Therefore, it will favor deeper zones. Although it is the stabilized pressure at each rate that is used to define the injectivity, the pressure transient measured after changing the injection flow rate should always be checked for signs of irregularity. These include rebounds, cycling, severe pump noise, most importantly, unlogged changes in pump rate. This could be caused by a failure of a valve in a rig pump. If such an irregularity is observed during the test, then the data is of low accuracy or totally invalid. The injection flow rates can be cross-checked using the fluid velocity determined from the spinner data measured in the cased hole at the top of each spinner profile. In wells that have a poor permeability, it can take a long time for the well to reach equilibrium. The zero pressure for the pressure test must match the stabilized pressure. In a well with poor permeability, it is very easy to overpressurize the formation, which will give inaccurate results. The pressure needs to be confirmed by pressures during heating. Wells with high permeability are slightly different. A value of gross permeability might not be very meaningful, as the value will depend on depth. Properties of the various feed and loss zones can be evaluated by a combination of enthalpy balance methods, wellbore fluid velocity profiles, and the productivity/injectivity index concept. Where an inflow of hotter fluid, either water or steam, is present during cold water injection, there is usually evidence in the form of a steeped temperature profile. The diagnostic test for an inflow is an increase in temperature in the isothermal section below the inferred inflow point if the injection rate is decreased. If the inflow temperature is known, the inflow rate can be easily calculated by heat and mass balance because the injection rate at the surface and the downhole temperatures above and below the inflow point are also known. The relevant enthalpy balance and mass balance equations can be seen on the screen. Once the flow rates from the formation are known using the injectivity/productivity concept with downhole pressure measurements, you can calculate either formation pressure constant productivity or productivity of an individual feed zone. If the formation pressure gradient is already known, these are the two equations to use. There's one for the upper zone and one for the lower zone. The formation pressure and pressure gradient are normally known from other wells. Therefore, an average value for productivity/injectivity can be obtained from multiple rate tests. A 3-rate test should provide sufficient data to solve the equations, even if both the injectivity/productivity and formation pressures are unknown. In practice, there are limitations to the application of this technique as a result from the accuracy and reliability of the data. Where mechanical downhole instruments are used, accuracy for the temperatures and pressure are typically not better than plus or minus 2 degrees Celsius and plus or minus 0.5 bar. Modern electronic instruments should have an accuracy almost an order of magnitude better than the older mechanical instruments. Therefore, they should be used whenever available. The field data may not truly be stable, and tests have shown that especially during the completion test period, the inflow temperature is not constant. The potential for error can be reduced by running the tests at several injection flows to provide check data. However, the overall results must be considered together with all the other available data for a more reliable interpretation of the field information. Wells with strong interzonal flow effects can be difficult to quench. If the upper zone is inflowing high enthalpy fluid during injection, the well can come under pressure quickly after stopping pumping because the wellbore rapidly fills with steam and gas. If the lower zone is relatively underpressured and permeable, it can be impossible to quench the upper zone when pumping water alone. At all flow rates, the upper zone continues to flow and the lower zone accepts all fluid. The measured injectivity of the well can be used to estimate the expected production of the well. It can be seen on the graph to the left. This relationship is approximated. It's accurate about 50% of the time and is convenient for sizing equipment for testing and can give an early indication of the well's potential. Wellbore heat transfer. The dominant method of heat transfer within the wellbore is convection. However, there is also some conduction that occurs. The heat transfer goes through the rock to the wellbore. This causes some of the water to be heated when it is injected to the well. You should assume that the heat transfer is normal to the axis of the well. The equation that is used to calculate the heat conduction is the equation listed below. At a distance, the temperature is the undisturbed reservoir temperature, and at the well phase temperature of the fluid. The conductive heat is done through heat transfer through unit length and is in the equation listed below. For time longer than a week, these are the following equations to use. And to calculate heat gain to the water, this is the equation you should use. Heating measurements. The downhole measurement performed after completion of drilling will be determined largely by the drilling technique and reservoir characteristics. During the heat-up period after drilling, data can be obtained that isn't available at any other time. This is only possible if corrected measurements are taken, especially for wells that are prone to being steam-filled. Testing is done 1 hour, then 2, 7, 28, and 60 days later if possible. High permeability wells will need more testing than wells with low permeability. The heating period can vary from a few hours to several months. At least 1 month is needed to collect most information. Low permeability wells usually heat slowly but evenly over 2 or 3 months. In some cases, it can take more than a year for the well to reach stable temperatures. Wells drilled into liquid or two-phase reservoirs with generally high permeability that develop strong interzonal flow will heat very quickly over the first few days and then show only slow changes with time in parts of the well that are unaffected by interzonal flow. For exploration wells, the well needs to be fully heated to stable formation conditions before the well is discharged. For new wells, there is a demand to flow as soon as possible to prove the production potential of the well. Following discharge, the well will be kept warm by a small bleed flow. Shallow temperatures inside the wellbore will be heated to the deep reservoir temperature. It may never be able to determine the true formation temperature as a result of this. Temperatures during heating. Following the completion of drilling and injection testing, the formations around the well are relatively cool. The impenetrable zones and cased-off sections have cooled conductively, and the permeable zones have cooled through the acceptance of water and drilling fluid. The fluid within the well can be heated through conduction from the formation and from the casings. There is also the formation of convection cells. However, it is important to note that convection outweighs conduction in terms of heat transfer in this. Pressure control point. The pressure pivot or control point is important to understanding well behavior. When the well is filled with liquid, the pressure gradient is controlled by the fluid temperature. When there is a single feed zone, pressure in the well at the depth of the feed zone is equal to the pressure of the formation. The pressure profile pivots about the feed depth, and the pivot point identifies the depth. When there are several feed zones, the pivot forms between the zones at an average. The lower zones are accepting and the upper zones are producing. Depth and pressure pivot points are the best indicators of formation pressures for multiple feed wells. You can see the pivot zones in the graph on the left. There are several characteristic features that provide information about the location of feed zones and true formation temperatures. These are zones of persistent temperature inversion associated with fluid losses while drilling, usually towards the bottom of the open hole interval, zones of rapid heating associated with fluid inflow, persistent isothermal or near isothermal sections indicating interzonal flow that enters and leaves the wellbore at either end of the linear profile, boiling point temperature curves, sections of slow conductive heating. In the case section of the well, there are also particular features that give us useful information about the reservoir. This includes linear conductive gradients, temperature peaks and inversions, boiling point temperature curves for reservoir pressures outside the casing. Gas pressure buildup. In some wells, non-condensable gases rapidly accumulate in the cased-off section when the well is shut. The pressure of this column can be used to locate the uppermost feed zone, as the gas column can only extend down the well to this level. After this, the gas will leak into the formation. The gas-liquid interface can identify the depth and pressure at this zone. When there are no gas leaks, the column can be used to find the formation temperature. Sometimes the temperatures are measured in both phase zones. This allows for more information to garner the real temperature. Vapor wells. This is where wells are completed into a vapor zone and steam rapidly fills the casing on termination of drilling. In this case, true formation temperatures cannot be determined. Heat transfer within the wellbore is much stronger than lateral heat conduction. Linear conductive profiles have been observed in wells where adjacent shallow wells show much structure to the shallow temperatures. If data on true formation conductions above the steam zones are required, then the well must be completed in stages. After the casing has been cemented, then the cement can be drilled out and filled with water and allowed to heat. True formation temperatures can be attained from temperature buildup measurements made over 2 or 3 days or by waiting longer for conditions to reach equilibrium. Convection cells. Convection cells are controlled by the configuration of casing and liners in the well. Continuous temperature profiles and flow meter measurements show that where lengths of plain liner are included in a string of otherwise perforated liner, convection cells will become established around the lengths of the plain liner. Fluid flows in one direction within the liner and returns in the annulus. Configurations with sections of plain liner between otherwise perforated liner should be avoided if possible. Where they are used, interpretation of the temperature data must make due allowance for the circulation cells that are generated. Variation in diameter of the wellbore outside the liner and even the perforation density can also result in the development of circulation cells with apparent isothermal temperatures as measured inside the liner. Injection performance. Injection well performance is an important metric. The bulk of geothermal process fluids that remain after extraction are injected back into the ground. Once the feed depth, formation pressure, and injectivity have been measured, the relationship between the injection flow rate and the wellhead pressure can be found. One of the equations important to determining this is the friction factor, which is calculated in the equation below. If the static gradient is needed, the equation is also demonstrated, and frictional loss is also seen below. For a geothermal well, the friction factor is normally within the range of 0.008 to 0.025. The equation to determine the flowing pressure in the well at the feed depth is displayed on the screen. For each section of the casing or liner, the pressure drop of the wellbore is also possible to be calculated with the following equation. The wellhead pressure is the summation of contributions from the different sections, and thus is displayed in the equations that follow, with C being an additional constant that needs to be calculated. Vapor-dominated systems are the last topic of this presentation. A vapor-dominated system contains fewer contrasts than a liquid-dominated one, as there are less features to observe. The exception to this is when there is the presence of superheat or the water is in a liquid form instead of a steam form. If the well is drilled with water or an aerated foam, then it is cold at the end of drilling. Changes during the heating of this wellbore will be similar to that of a liquid-dominated reservoir. Inside the well, a column of water will be present. The injectivity can be measured by pumping in cold water, just like in a liquid-dominated well. As the water heats within the well, it will turn to steam. If the well was drilled with air only, it will not be cold at the end of drilling. Once the permeability is found, drilling continues with a controlled discharge of steam. This provides a direct observation of permeability, as the gain in flow gives its flow combined with other measured metrics. At the feed zones, the pressure of the water in the well must fall below that of the steam reservoir to allow the steam to enter. Well will have a passive water column for years until the water pressure falls enough that it can discharge. Thank you for watching this presentation on well completions. There is a quiz that is based off the material covered in this video on Canvas.